Here we want to plot the motion graphs for balls which are dropped from rest, thrown into the air, and bounced off the ground. This time, the variable that I'm using for position is y instead of x. X is typically used for something that would be horizontal, or perhaps a ramp that's just tilted a little bit. Y is typically used for position in the vertical dimension. So that would be great for an object which is thrown up into the air. But first we're going to drop the ball from rest. Now, it can be tough to know what the motion graph is supposed to look like for something like that. So that's where a motion map could help us connect the concept of how the ball falls to what the motion graph should actually look like. Let's say that the time axis represents the elevation of the ground. And this is green to represent grass. We're going to take a red ball here and let's start it up high. So we're going to release it from a high point and let it fall down to the ground. Now keep in mind that this is not an x-axis, it's not a position axis, it's a time axis. And the ball is going to fall straight down. And so let's drop the ball straight down so that it lands on the ground below. What would the motion map for that look like? Go ahead and sketch yourself a motion map on the side because we can use that motion map, like I did before, to construct the motion graph. So as I showed in a previous video, the motion map for a ball which is being dropped could look something like this. The spacing between the positions has to get larger and larger as time goes on. And we should also give it some velocity arrows. And those arrows should get larger and larger as time goes on. Now these are supposed to be snapshots in time of where the ball is located of regular time intervals. So this could be t equals 0. Here we've got t equals 1, then t equals 2, then t equals 3. So if you trace the object over, it would be located up here at t equals 0. Now at t equals 1, we want it to still be pretty high up there. At t equals 2, it can fall more. And then at t equals 3, it should be on the ground. So we're actually looking for a parabola shape here. And that's the graph. All right, so now we want to see what facts we can extract from the situation in order to plot the velocity graph. So one thing about a ball that's dropped from rest is rest implies the velocity was 0. So if the velocity is 0, at time 0, we want to start off here. Now this ball does pick up speed. It starts going faster and faster in the negative direction. We want that direction to be important in our velocity graph. We want it to be represented by the velocity graph. So since our ball falls down rather than up, we're going to want our velocity to go down as time goes on. And it'll go down in a linear fashion. Now let's draw the acceleration. The acceleration is the slope of the graph above. So it's got a negative slope, but it is a constant slope throughout the entire time interval. And for that reason, we're going to make our acceleration just a constant negative value. And another way to understand how we should graph the acceleration is this. Earth pulls down on objects that are in free fall. It pulls down all the time, no matter where the object is and no matter what it's doing. And so the acceleration kind of goes along with the pull of Earth. And since that pull is just constant, the acceleration is constant too. All right, now what we'd like to do is throw our ball into the air. Now for a motion map of throwing the ball, somebody's got to supply the energy to the ball to get it to go in the upward direction. And we want a motion map that looks like this. Where it eventually reaches a peak where the ball just stops for an instant. Then we want it to turn around and come back down. Okay, that's just a qualitative motion map of what's happening in this situation. You throw the ball up, it reaches a peak, and then it comes back down. We now want to transfer these dots to our graph. And what it ends up looking like is just the classic parabola you see whenever a ball is thrown as a projectile into space. It actually makes an upside down parabola. The top of which is called the peak. All right, so when we want to draw our velocity graph, we actually already have a lot of it drawn already. We drew half of the trajectory in this first graph right here. So let's just copy that, right? At the peak, the velocity of the object is 0. It's neither moving up nor down. And so we actually want to be able to connect them to. Those are important points in the motion of the object. Then we want the velocity to become increasingly negative as time goes on. But what happened before that? Well, when you're here on the parabola, if you're walking along the parabola, are you going up or down at this time? What's the slope like? Well, the slope is positive, right? Over here, on the right side, it's negative. So for every step you take in the positive time direction, you would be falling, right? So that's why it's negative. But over here, every step you take in the positive time direction, you're going to be going up. And where is it steepest? Is it steepest at the start, or is it steepest toward the peak? Well, I think we all can agree that if we were walking up this mountain, the time that would be most difficult to walk would be actually toward the start of the motion. And so that's actually when the velocity is going to be the highest too. And that's what it looks like. So when we throw a ball, we throw it with its highest speed at the start. You can see because the arrow is really long there, right? Then as you go up in the air, the ball slows down more and more until it eventually stops. That's this point on the velocity graph. Then it turns around and starts going more and more into the negative direction, and that is this part of the velocity graph. Nothing more than an extension of what we had done over here to the left. Now we want a bouncing ball. So in this case, what's going to happen as far as a motion map goes is we release the ball from rest. It starts picking up speed in the negative direction. So let's draw those velocity arrows. Now it's going quite fast. And it's going to hit the ground. And then it's going to bounce back. And then go up. Let's see if we can project that kind of idea onto the graph. So start up high. Let it come down like a parabola. Then it's going to strike ground and then come back up. And when it comes back up, it'll just go right back into free fall. Let's connect those points. All right, what does our velocity look like here? It's dropped from rest. Velocity goes more and more negative. And then here something happens. It makes contact with the ground. So before the impact, the ball was moving very fast in the negative direction. During impact, it's not sure what way it's going, but then directly after impact, it's moving very fast in the positive y direction. We want to show that with the velocity graph. So let it go to a really large negative value. And then after a short time, let it switch to a high positive value. And then it can go down from there. Now what happens exactly between those two extremes is something that we'll study later in the course when we look at collisions. For now, what we could do is we could simply put an open dot here and here to say that the velocity is just not defined at that time. It makes a sudden switch. Now that's a mathematical model. That's not what really happens in the real world. In the real world, what happens is it takes time for that change to happen. And it might look something like that. If we use a motion detector on the ball, we can see this kind of graph be developed. But a lot of times we just want to simplify things with the mathematics, so it would be okay to use this open dot idea. So that's going to be our graph of the velocity for a bouncing ball. All right, now for the accelerations of them two, go ahead and guess what you think the accelerations look like for these two cases. It's a little tricky. Remember that the acceleration at any given time is the slope of the velocity graph. Okay, so if you did this one correctly, what we would actually want is just a nice, consistent, negative acceleration throughout the entire flight of the ball. The slope of this is just constant. It's a straight line, so same slope everywhere, and it's a negative slope. And like I was saying before, Earth always pulls down for free fall. This one's a little bit more tricky and a little bit more complicated. The acceleration is negative for that whole time, and it becomes negative after the collision. Now, what exactly happens during the collision is a little bit of an advanced topic. What we can do for now is we can just put an open dot there and say, the velocity suddenly switches from negative to positive. So we could say there's no defined acceleration there. But in the future, we will look more closely at exactly what actually happens there. Just to give you a preview, a hint of it, is that the acceleration jumps up to a high positive value for a brief time. And that's what accounts for the velocity switching from negative to positive during impact.